Imagine a computer that learns like you do, from experience. It doesn't just follow instructions, it understands patterns and makes decisions based on what it senses. That's the promise of neuromorphic computing, a revolutionary approach to artificial intelligence. Unlike traditional computers that process information sequentially, neuromorphic systems mimic the structure and function of the human brain. Traditional computers are very good at tasks like calculations and data storage. However, they struggle with tasks that humans find easy, like recognizing faces or understanding language. This is where neuromorphic computing comes in. Neuromorphic computing aims to overcome these limitations by using artificial neurons and synapses to process information. This approach allows for parallel processing similar to how our brains work. This makes neuromorphic systems potentially more efficient and adaptable than traditional computers, especially for tasks involving complex patterns and real-time learning. The human brain is an incredibly complex organ composed of billions of interconnected neurons. Each neuron acts like a tiny switch, receiving signals from other neurons through synapses. When a neuron receives enough signals, it fires, sending its own signal to other neurons. Neuromorphic computing draws inspiration from this structure. It uses artificial neurons and synapses to create networks that can process information in a similar way to the brain. This allows neuromorphic systems to learn from data and adapt to new situations, just like humans do. This biological inspiration gives neuromorphic computing a significant edge in tasks like image recognition, natural language processing, and robotics. These are areas where traditional computers often struggle due to their reliance on rigid algorithms and sequential processing. There are several approaches to building neuromorphic systems, each with its own advantages and challenges. Analog neuromorphic systems use electronic circuits that directly mimic the behavior of neurons and synapses. Digital systems, on the other hand, represent neural activity using digital signals, offering greater flexibility and scalability. Mixed-mode systems combine the best of both worlds, using analog circuits for efficient computation and digital circuits for communication and control. Finally, software systems simulate neural networks on traditional computers, allowing researchers to experiment with different architectures and algorithms. These different approaches highlight the versatility of neuromorphic computing. Researchers are constantly developing new ways to build and improve these systems, pushing the boundaries of artificial intelligence. Section 4: Sensing, Thinking, Acting. Neuromorphic systems are particularly well suited for tasks that involve perception, motor control, and multisensory integration. For instance, they can be used to develop artificial vision systems that can recognize objects and faces in real time, just like the human visual system. In robotics, neuromorphic systems can enable robots to interact with their environment more naturally and adaptively, learning from their experiences and adjusting their movements accordingly. They can also be used to create brain-computer interfaces, allowing humans to control prosthetic limbs or communicate with computers using their thoughts. The ability to process information from multiple senses simultaneously, just like our brains do, makes neuromorphic systems ideal for applications requiring a deep understanding of the environment. This includes autonomous driving, where cars need to process data from cameras, LiDAR, and other sensors to navigate safely. Section 5: The Future of Intelligence. Neuromorphic computing is still a relatively young field, but it has the potential to revolutionize artificial intelligence. As these systems continue to develop, we can expect to see them used in a wide range of applications, from self-driving cars and medical diagnosis to personalized medicine and smart cities. Imagine a world where computers can learn like humans, adapt to new situations, and solve complex problems with ease. This is the future that neuromorphic computing promises. While challenges remain in terms of hardware development and algorithm design, the future of intelligence is looking increasingly neuromorphic.